Okay, we've been talking chapter 17, I think. Uh we're talking about electrochemistry here, and we were talking about last time our galvanic cells. Remember that again, the main parts of our galvanic cell, we have an anode, we have a cathode, we have a salt bridge that ties them together here or ties them together. We have an electrode and connect it through a wire, some voltage happening here. Remember that the anode is where oxidation occurs, and the cathode is where reduction occurs. And electrons travel obviously from our anode to our cathode in this case. Again, there's sort of a cell potential difference that sort of pulls those negatively charged electrons to the other side, as we talked about last time as well. The salt bridge is really important as it sort of keeps the balance of charge where it needs to be to complete the circuit. It prevents really a buildup of sort of the wrong charge on the wrong sides that will keep the electrons from sort of traveling. We could calculate our E of the cell as we've been talking about a couple of ways. Once again, you can take your cathode minus your anode. And as we talked about a number of times, again, the idea there is the minus in this formula will actually change the sign for you as one of the reactions, which is the anode reaction, and that's the oxidation reaction. You do need to change the sign of the SRP value that you find in the table. So if you do not want to worry about changing the sign, as we talked about, you want to definitely subtract those two values. And again, the minus there will change the sign for you. If you do want to change the sign, then you should roll again, as we talked about, with really just adding them together. So if you change the sign yourself, you then should add them. If you don't change the sign, then you should leave the minus there, so it'll do it for you. In addition, we sort of related our voltage to our thermodynamic properties like NFE. And of course, that would be delta G at the beginning there and probably look a little better, I suppose. Well, delta G there. So our Gibbs free energy is equal to minus NFE. Again, N is the number of electrons being transferred from the anode to the cathode. F is Faraday's constant, a 96,500 number. E is our E of our cell here. And as we talked about, positive value for cell voltage will result in a negative value for delta G, which means the reaction should be spontaneous. We also saw a couple of other equations like E naught is equal to RT and F natural log of K. And this involves the equilibrium constant. And that really is from RE naught of the cell minus RT and F natural log of Q. And that is the Nernst equation over here. This is the one, obviously, that involves the equilibrium constant. This is under sort of non-standard conditions. So as we talked about, your E of the cell, if you play with concentrations or pressures, it's possible to maybe turn a non-spontaneous reaction into a spontaneous reaction. Remember, something's in standard conditions, all the molarities are one, all the pressures are 1 atmosphere, and molarity is 1 molar, temperature is 25 degrees Celsius. So again, if we have a non-standard condition, we could calculate our E of the cell. This is pretty much what we got up there. Remember, the R here, though, is the sort of one with energy that's here. And our Q is our products over reactants at equilibrium. E equals 0, and Q will equal K, which if we rearrange will get us back to this equation here. Any questions on any of that stuff there? I think we talked about last time. So I think we did a Nernst equation example there. So I think we have perhaps this one to go. For the following, forget about balancing the equation. Why don't we just calculate E and K for this reaction, see what you come up with here. Okay, so let's take a look. So once again here, equilibrium constant involved, which narrows down the equation there to our RT-NF natural log of K. Again, remember that you could get this one also from the Nernst equation, which looks like this. Again, this is going to be 0. This will become K. If you just bring this whole thing to the other side, again, it's actually positive here, not a negative. So obviously our temperature, still 273 action there, 298. Our Faraday's constant, 96,500, I think we've been using. And in this case, if we look at it, we do need probably a couple of electrons there. So N should equal 2 in this case. Now, R is a constant, which is 8.314. We do want to figure out our E of our cell, which again is our E of our cathode minus our E of our anode. In this particular case, if we're not sure, you can just look at the chromium, probably it's the easiest. +2, it's a +3. So again, it is, if you sort of travel the number line there, becoming more positive and going through oxidation. That means the chromium here is our anode. And by default, there our other guy there would be our cathode. Remember, in this case, we are given an equation, so we do need to look at the equation and see what is going on. And that is, I think, what's going on in this case. So we can calculate our E of our cell. Once again, here, I'm not going to change the sign, so I'm going to subtract. And by subtracting, it will change the sign for me here. And if I do that there, 0.17 minus and minus 0.5, looks like a 0.67 volts in this case. That's pretty much everything I need. We'll have 0.67 volts equals our 8.314, which is our temperature of 298 divided by our 2 moles and our constant there, 96,500. And that's going to be the natural log of K in this case. So I'm going to pretty much multiply what's on the bottom to the other side, and then I'm going to come back and divide by what's on the top there to the other side. So I'm going to take 0.67 and times it by 2. It equals, times it by 96,500. It equals, I'm now going to divide by what's on top. Divided by 8.314, it equals, and divide by a 298er there. And that's going to give me, when I do all that good stuff, the natural log of K will equal something like 52.192. To get rid of the natural log, we're going to take the E of both sides here. We're not going to insert any type of negative or anything like that. So we're just going to take whatever the number is. And that will give us a K value here, 4.6 times 10 to the 22 in this particular case. Yeah. Any questions on that there? Things do sort of make sense. We hit a positive voltage, which means it should be a spontaneous reaction. And because it's a spontaneous reaction, it should probably be heading towards the product side. And because it's heading towards the product side, we should have more products and reactants, and we should end up with a large value for K in this case. Yeah. Any questions on that there? Yeah. I just looked at the half reaction. So remember, when we add these guys together, we need to balance out the electrons. So we had to multiply the bottom guy by 2, and that will give us the same number of electrons at each. And it is, again, just the electrons that are being transferred from the anode to the cathode, so we don't add them together or anything like that. So it's just 2 is basically leaving the chromium and being accepted by the other guys. So that's where the N would come from. Other question? So that would also mean probably we need some 2s up here if we really balance it up. All right, any questions on any of those calculations? All right. Okay, then let us continue and talk about batteries for a bit here. Good talk. A battery is basically a galvanic cell or a series of galvanic cells that's used as a source of direct electrical current at a constant voltage. They're very similar to sort of a traditional galvanic cell you could build in the lab, except with all the sloshings, chemicals, and the beakers. They're sort of self-contained with inside. They have some other stuff that act like a sort of salt bridge and keeps everything flowing. So let's take a look at a few different types of batteries. And I would say in general, what you need to know is just a general idea of batteries and sort of how they're similar, maybe a little bit different from a traditional galvanic cell. I'm not going to ask you, to write the half reactions or anything like that for any particular type of battery. But if we look at this guy here, this is a dry cell, and it's a cell without any type of fluid component. And I'm going to go with Duracell perhaps on this one here. And there is a positive side, right? And a negative side, sort of your anode and your cathode, right? Connected by a wire when you put it into the battery compartment, right? So we have basically the redox reaction happening, electrons heading, towards your cathode side, if you will. In this case, our anode is a zinc can in contact with MnO2, which is an electrolyte solution. We also have a carbon rod that's inside there that's acting as our cathode here. This type of battery will essentially give you 1.5 volts. They come in different sizes, right? They have AA, right? AAA, C, D, all those type of sizes. They all give the same voltage, just bigger, has the ability to sort of last a little bit longer, right? Keep this sort of reaction going. In this case, this interior here is sort of acting as your salt bridge. It has an electrolyte solution, kind of like we put in a salt bridge, like sodium chloride or something like that. But this paste, again, sort of keeps that buildup of positive charge or negative charge sort of happening. So if we look at the anode side here, we see our zinc going from 0 basically to +2, being oxidized in this particular case. And on our, excuse me, on our cathode side, we do see a sort of gaining of electrons there as it goes from like a +4 action. That's like 6, that's a +3 sort of situation happening there. Overall, this is the overall reaction that is occurring. This type of cell obviously is used a lot for a lot of electronic devices. And again, it's just like a sort of traditional galvanic cell in a sense that, as we talked about, if you put your battery in backwards, it doesn't work very well, right? Because you have a non-spontaneous process occurring. You flip it around the right way, you get your anode and your cathode sort of in the right orientation, you will actually get the battery to work. Same thing with your galvanic cell. You can have negative voltage, but if you swap those guys around, you will have positive voltage. Another type of battery is a mercury type battery. And a mercury battery used a lot in medicine and electronic devices. It's more expensive than the previous type of battery. It also has sort of a zinc as your anode. It's in contact with a really strongly alkaline electrolyte like potassium hydroxide. Alkaline means basic, so a really strong base is here again, sort of being used like a salt bridge in that sense. Um, and we have no change really in the electrolyte composition over time. And that's really important in terms of long lasting for batteries and also in terms of sort of being able to recharge batteries and things of that nature. If you end up with sort of solids and stuff like that in your overall reaction, that's really well for sort of long life and stuff like that, because things really don't sort of degrade all that much. So they hang around for a pretty long time and they're able to be sort of recharged multiple times. The overall reaction involves only solid substances, which is sort of the key to sort of why it's sort of long lasting. Here you get a little less of a voltage, 1.35. And again, we see sort of our zinc going from 0 to +2. That's our mercury +2 to 0, again being reduced in this particular case. So again, this oxidation reduction reaction that's sort of happening here. Now, a lead storage battery is the ones we use in automobiles, and there are basically a bunch of series of cells sort of put together. Each of those guys basically produce about 2 volts, and with 6 of them in line, will give you 12 volts overall, which is enough to start your car and get everything going. Except if you're late that day, then it will not start, of course. Um, but it is rechargeable. And if you've ever had that, your car didn't start and you had to jump it, they tell you, right, leave it running for a bit, and maybe you'll be in good shape and it'll sort of recharge itself. And again, we could check healthy batteries by looking at the density. Good battery has 1.2 grams per milliliter electrolytes. In cold weather, that electrolyte sometimes gets a little bit more viscous, which means a little bit lower sort of output. And this is sort of a cross section of a traditional car battery here. And again, you can see it's really a bunch of plates here and cells in a row in a series. Again, each of them giving you your 2 volts. You have your positive cathode here, right? And your negative anode. And they always like, which one do I connect to which? The red or the black to which one? A lot of times nowadays, sometimes your battery may not even be in your engine. Sometimes they throw it in the trunk these days, under your seat and stuff like that. But you'll have like the little sort of cathode or anode part there that you could jump it with. It has obviously a very strong sulfuric acid sort of solution, which is what sometimes people refer to as battery acid, right? That comes out of sort of batteries and stuff like that. Um, Here again, we see a lot of solid, which is very good, as I was mentioning, in terms of being sort of rechargeable. Here, our lead is going from 0 to +2. And our lead here on this side is going from +4 to over here. We have +2 in this case again, gaining some electrons on that part. We also have things in the cars, right? So the battery doesn't just drain out, right? Alternators and those type of things to vary the current, so we don't just drain it. And another type of battery is a lithium, solid-state lithium battery. It has an anode that is some type of carbon or graphite type material that has actually holes in it that allows the lithium, as they kind of lose electrons, to sort of migrate across. The cathode is some type of transition metal that could hold the lithium ions that are coming across. It can be recharged hundreds of times without deterioration. It's also a very light metal, which is why they use it sometimes, right, in tools and those kind of battery packs and stuff like that as lithium type of batteries. Very light type of battery, can be recharged lots and lots of times. Now, a fuel cell is not necessarily a traditional battery, but it does also sort of function like a battery. And years ago, that's basically what they wanted to make cars out of, I guess, or make cars use, I guess is a better way of putting that. Hydrogen sort of fuel cells. The reason for that is, as we can see in the overall reaction, you pretty much make water, which is nice and clean and stuff like that. In order for this to work, you really do need a supply of hydrogen and oxygen being sort of funneled in there for this sort of fuel cell to work. Here we see our hydrogen going from 0 to +1 being oxidized, oxygen going from 0 to -2 being reduced in this case. And again, the nice thing about that is obviously you just make water. Hydrogen is not necessarily like our gas, right? In terms of how you fill it up in stations and stuff like that. So we've obviously moved to a hybrid and now to electric, straight electric. And sort of gave up a little bit on that. I think Toyota still has that Mirai, I think, is it, or something like that? That it's like a hydrogen type of car and stuff like that. You got to find the hydrogen station somewhere near where you live. All right, so that's a little bit about batteries. And again, like I said, batteries are pretty much galvanic cells. They obviously have solid components as opposed to liquid components, but the function of it is really still a redox reaction where obviously you're using those electrons to power some type of device. So let's talk a little bit about corrosion as well and what's happening with when something goes through corrosion. Corrosion is really returning metals to their natural state. About a fifth of steel production is to replace metals that have basically rusted out. So what happens is all metals that have a SRP value, a standard reduction potential value, less positive than oxygen, is susceptible to going through corrosion. And that's because if you take a metal that has an SRP value less positive than oxygen, that means oxygen would be my anode or cathode in this case. The more positive one is the cathode, right? So what that means is when you get a metal and oxygen together and oxygen is more positive, it's going to act as the cathode, which means it's going to have reduction happening. And our poor metal over here is going to act as the anode, and we'll have oxidation occurring basically. And that's basically what happens with corrosion. So any metal that basically will do that will basically set up sort of like a galvanic cell where oxygen is going to act as the cathode. It's going to draw the electrons away from the metal, and that's going to cause sufficient corrosion basically to occur. And you will get, obviously, if in that case, a positive value for E. And because you'll get a positive value for E, that means it'll be pretty spontaneous. So it will just happen, right? And that metal will go through corrosion. Now, not all sort of corrosion is necessarily a bad thing. So sometimes metals can make a thin oxide that actually can protect further metals from going through oxidation. So certain metals, when they go through oxidation, can form this sort of layer that gets oxidized. And although the top layer that gets oxidized, it does end up kind of protecting what's underneath that layer from further oxidation. So for example, aluminum is an example of that. When it goes through oxidation, it makes this aluminum oxide, which sort of makes a nice layer and protects the metal that's underneath it. Now, iron does the same thing. The problem with iron is it tends to fall off. And that's what rust is basically, right? So when iron goes and does that, it makes that layer, it falls off, exposes brand new, obviously, metal there to further go through corrosion until it kind of corrodes all the way through, right? You can put your finger through the piece of metal, right? It's all rusted out and it goes all the way through. So in some cases, not such a good thing, as in the case of iron, but in some cases, it can be sort of protective. Copper, as we may know, forms that greenish sort of patina color, which can make things more expensive, right? As they sort of patinas. Silver will tarnish, make some silver sulfide. Gold with 1.5 voltage for its SRP value is larger and more positive than oxygen. So gold does not go through oxidation. And that's because when you pop oxygen and gold together, gold actually will now become the cathode because it's more positive, and this will be my anode, and thus all oxidation will happen there at oxygen, and the gold will pretty much be okay, right? Which is why it's one of those noble type metals, right? Very unreactive. And that's one of the reasons for it. Now, steel, as I mentioned before, has these stress sort of points. And as we go through sort of the oxidation process, you basically just need a little bit of iron, some moisture, and some oxygen, and you're good to go. So it's got these sort of non-uniform points where really moisture could kind of sit in, and that's going to really sort of funnel the rusting occurring. What actually will happen is iron will actually oxidize to iron 2, and then after that, it will then be able to react with oxygen and actually form iron 3 oxide, which is rust. And that's what we see here. Has these sort of non-uniform points, a great place for sort of moisture to sit, allowing the oxygen and the iron basically to react with each other and obviously make rust, which, as we just talked about, can fall off and allow that process to basically occur again, costing lots of money here. So we actually see iron go to iron 2, get further oxidized to iron 3, and then combine with oxygen there to make our rust. Now, there are ways that we can prevent corrosion, and a couple of ways to prevent corrosion are what we see here. We could apply some type of coating. You could apply paint or something like that to the metal, hence the name Rust-Oleum paint, right? To prevent rusting, right? All the spray cans that you can buy. You could also use something like chromium and tin is used to plate steel. We can also galvanize, which is basically a mixture of oxide and carbonate coating. And since zinc is more active metal than iron, we actually get some protection of our iron. So when we do that and we compare these two and we use a little bit of zinc in there with our iron, zinc has an SRP value of minus 0.76 versus irons, which is minus 0.44. When comparing those two, that will then turn really our iron into the cathode, and all the bad oxidation and stuff that's going to happen at the anode will happen at the zinc. So zinc is sort of acting as a sacrificial sort of metal to protect the iron. By doing so, all the oxidation and stuff will occur basically on that zinc. Alloying as well prevents corrosion. You could add some other elements as well, which will change the SRP potential to more of a noble gas situation, which again will prevent a significant amount of corrosion from happening. And that is also what can happen when we have like a storage tank that's been buried underground. And if you have a storage tank that's been buried underground, obviously there's a lot of moisture and stuff underneath. You can hang a magnesium wire to this tank or pipeline, and magnesium is a better reducing agent than iron. And remember, our reducing agent gets oxidized. So again, here, if magnesium is a better reducing agent, when those two get together, it is going to be the magnesium that gets oxidized. The iron will be our cathode or get reduced in this case. And that allows, again, all the bad stuff basically to happen to the magnesium, protecting your tank that you buried underground. Titanium's used in ship hulls to prevent corrosion through the sea air. And that's what we see here, all the oxidation happening over here, so that you don't every week have to dig up your tank that you buried in the ground, which you would not want to actually do. Any question on corrosion? So for corrosion, you need to know what it is, a couple of ways to prevent it. Yes, that along with obviously how a battery and a galvanic cell are similar and different. That's probably the same question on the next exam, I imagine. Maybe question 6. Imagine that's what that's going to be. Any questions on that there? Maybe it's question 7. I don't know. We'll see where it ends up. All right. So the last thing we're going to talk about here in this chapter is electrolysis. And electrolysis is the process in which electrical energy is used to cause a non-spontaneous reaction to basically occur. And in this case, if we take something like sodium chloride, and we can basically break it back down into its elements through the process of electrolysis by adding either an external sort of battery or power source to do so. So what happens in this oxidation process or this electrolysis process is actually opposite of what happens when we put something like sodium chloride together. So when we put sodium chloride together, we are taking sodium and some chlorine gas, and we're making a little sodium chloride action happening there when we put it together here. And maybe a little balancing, good chemistry person. And in this particular case, when we actually put it together, we have sodium's going from 0 to +1, right? And chlorine's going from 0 to -1. In this particular case, my anode is which one? It is the sodium, right? That is what is going through oxidation. The chlorine here is being reduced and would be my cathode in this case, right? And that's what we would expect in the formation of an ionic compound like this, as it is really the metal giving the electrons back over to the nonmetal. But when we do electrolysis, which is a non-spontaneous process, because we've all had sodium chloride, right? And you could heat the heck out of it. I'll say the right word there. You heat the heck out of it, and it will not break back apart, right, spontaneously into chlorine gas and sodium, which is really good, especially if you're eating on fries or something like that, right? You don't get any of those toxic stuff coming back at you. But we can make this process occur sort of non-spontaneously by applying an external current and energy to do that. And if we're doing sort of the electrolysis of it, we're actually going to be starting with the sodium chloride. And we're going to break it back apart really into its elements, sodium and chlorine here. And when we're going in this direction, which is what's happening with electrolysis, we are actually starting with sodium with a +1, chloride with a -1, 0, and 0. Now going in the backwards direction here through electrolysis, which one is being oxidized? It is actually the chloride here. It's going from -1 to 0, right? Becoming more positive in that case and being oxidized. So this is really our anode in this case, going in the opposite direction where oxidation is going to occur. And it's actually the sodium that's going to be our cathode in this case. And that is where reduction is going to occur. And we see that with the sodium starting at +1, ending at 0, becoming more negative here and being reduced in that case. So through the electrolysis process, we actually do have our sort of half reactions reversed because we're going in the opposite direction of this reaction. So that's why what we see here when we look at the oxidation half reaction, it is the chloride losing electrons and becoming chlorine gas back to its sort of elementary state. Electrons coming over to the other side where the electrons will join up with those sodium ions and reduce it back down, in this case, to a little bit of sodium liquid. So the electrolysis sort of process, which you could think of as kind of like the opposite, you could think of like, I guess you could think of the original one as like a synthesis combination reaction, and this more like a decomposition sort of reaction heading in the opposite direction. Those anodes and cathodes basically switch places because you're going backwards, basically, in this case. Any question on that there? Now, if we look at something like water, it's same idea. When we make water or put water together, we are taking H2 plus a little bit of O2, making our friend H2O. And once again, sort of putting water together, that's a 0, that's a 0, that's a +1 and a -2. Hydrogen is going from 0 to +1. It is being oxidized and would be considered our anode in this case. Oxygen is being reduced in this case, which would be our cathode. So again, putting it together, it's sort of what we normally would sort of visualize here. But you can break apart water back into its elements through a process known as the electrolysis of water by running electrical current through it. Frankly, all you need is like a 9-volt battery, a little acidic water, and a couple of leads and stuff, and you'll be able to do it. And actually, one of my classes actually does that experiment. They hook up a 9-volt battery and run electrolysis of water. So if we're going in the opposite direction here, where we're starting with water and breaking it back there to its elements, we're again starting with +1 and -2, ending with 0. So again, in this case, it is our oxygen that is going from -2 to 0, becoming more positive. That's actually our anode and being oxidized. It is our hydrogen here that will act as our cathode and being reduced as it goes from +1 to 0, becoming more negative in this case. And that is what we see here when we look at the half reactions. we take a look at this experiment, which you could do, and we end up getting bubbles happening, which is our hydrogen gas and oxygen gas as we break apart water in the empty area there in the test tube. It is not really empty. That is where our gas is, right? So that is where our hydrogen gas and oxygen gas is. Why is there more hydrogen than oxygen? It is H2O, so you got twice as much, right? Oxygen as you do, twice as much hydrogen as you do oxygen, so you will collect that when you break it back apart. And that's what we see in this particular case. Now, when they are talking about, especially when you're doing sort of electrolysis problems that involve the electrolysis of water, a lot of times they may not even mention water. They'll mention something like this, like you have a dilute sulfuric acid solution or some type of dilute acid solution that you're doing. And usually in electrolysis sort of problems, that pretty much means you're doing the electrolysis of water, which would be these two half reactions. So sometimes they really won't kind of just straight out tell you, hey, this is like the electrolysis of water type problem. They'll mention something like sulfuric acid, dilute sulfuric acid solution, running a current across it. And basically that's going to be the electrolysis of water. The reason you need that is, frankly, you do need to beef up a little bit of the H plus concentration in there to allow this sort of to work very well and more efficiently. So typically this is done with what's sometimes referred to as more acidic water than just regular water. And again, that sort of extra H plus in there allows for this process basically to take place pretty good in that particular case. Any questions on that there? And it helps out over here, as you can see, as it's going to gain with those H pluses as those electrons sort of come in. So when we have electrolysis sort of problems, there's a few things that we sometimes want to figure out, and there's usually sort of a set pathway to calculate these type of problems. And usually they will give you the current that the electrolysis cell is running at. And a current's usually given to you in amperage, and a charge or a coulomb here is equal to an amperage times a second. So usually A is equal to C over S. And that's sort of what they'll give you, sort of the current in. They'll also tell you, hey, you ran the cell for 5 hours, 2 hours, 22 minutes, whatever it may be. What you want to do is then take the charge in coulombs. You want to divide it by Faraday's constant. So what you're going to essentially do is, a lot of times in these problems, you will have really the coulombs per second. You usually will times it by how long you ran your cell in seconds so that the units cancel out. That will usually give you a coulomb of charge, which that is what they're talking about here, using really Faraday's constant. And 96,500 coulombs per mole of electron. Coulombs will cancel. You'll end up with moles of electrons at this point. Now, this is where the problem doesn't really change too much, but this is where the half reactions come into play. And what you would do is you would have in this type of cell an anode half reaction and a cathode half reaction. And basically you would use the moles of electrons and do a little stoichiometry. And you would take the moles of electrons in the half reaction to the moles of, whatever you're looking for, like an element that you're looking for, like, for example, hydrogen, or maybe you're looking for sodium or something like that. So you'd be looking for that in the half reaction. What that's going to do is essentially give you the moles of your element that you broke the thing back down into. At this point, it does vary depending on the problem. If you are looking for maybe how many grams you're going to like plate out or something like that, you would take your moles, a little molar mass, right? Which is grams per mole, and you can figure out how many grams you would actually get as a result of this. But you could have something like are hydrogen and oxygen, which are gases. And sometimes with gases, we're not necessarily interested in grams, but we're interested in how much volume of a gas that we might collect. And that's going to throw us back to a classic PV equals nRT, a little ideal gas law situation. Yeah. If you remember, pressure is in atmospheres, volume is in liters, N is moles. R is the gas constant. Remember, if you are using the ideal gas law, that is the 0.08206 number, not the one with energy. I'll tell you how much just wrote there. And our temperature there is in Kelvin. So if you're dealing with a gas, you may be given all that information, and you would solve for volume. nRT over P. So that's also a very common sort of ending to these type of problems. If you're dealing with a gas, kind of go into the ideal gas law. Any questions on that? Variation of this problem is they'll tell you maybe how much grams you produce in the cell or how much volume of a gas you collected, and you work your way backwards and figure out maybe how long the cell was running for, or what the amperage was, kind of going in the backwards direction. It's basically the same calculation, just running backwards. Any questions on that there? So let's take a look at one here together. We'll start with this one here, I think. Now, if we have this sort of electrolysis cell and we want to know how much calcium would we produce if we ran a cell with calcium chloride, if the current 0.452 amperage is passed through the cell at 1.5 hours. So remember that what we're doing in this case is, again, we're starting with the calcium chloride, and we are going to break it into calcium and some chlorine gas here, right? And again, we're going from +2, -1, 0, and 0 in this case, as we kind of go to the back end here. And in this case, it is our calcium that's going from +2 to 0 that is being reduced and would be our cathode. It is our chloride that's going from -1 to 0 and becoming more positive, and would be our anode in this case. So you again want to make sure that you do get sort of the correct half reactions happening. And again, these are the correct half reactions that's happening here. Once again, we're starting with the ions and kind of going to sort of the elemental form of them that have no charge or oxidation state. Any questions on that there? All right, so let's talk about how we want to do this calculation. So for example, we know that we're going to run this guy for 1.5 hours. We know we have a 0.452 amperage, and that again is the same as 0.452 coulombs per second. And I'm just going to change my amperage into those units so that things cancel out correctly. And clearly I can see I have seconds there, which means I do need to convert my time into seconds. So 1 hour is like 3,600 seconds, I think so. So that will give us 1.5 times 3,600 gives us 5,400 seconds. All right, so now we got our time and we really have our amperage and sort of the right units. We're just going to multiply those two together. So we're going to take 5,400 seconds, which is how long we're running the cell for. We're going to times it by the amperage that has been converted into coulombs per second, which is basically the same number. And we will end up with here 2440.8 coulombs. At this point, we're then going to actually use Faraday's constant to convert this into basically moles of electrons. So we're going to divide here by Faraday's constant in this case, and that would be 96,500 coulombs per mole of electron. Coulombs are going to cancel, and once again, that is basically Faraday's constant that we've used previously. So if we take that, divide it by 96,500, That is going to get us here 0.025, and we'll call it 3 moles of electrons. Any questions up to that point? I would say that's pretty standard fare in terms of these type of problems, in terms of what you need to do to get yourself to moles of electron. Now, in this particular case, we're interested in calcium. So that is where our half reactions are going to be important. And if we look at the calcium half reaction, we see for every 2 moles of electrons, we get 1 mole of calcium out. So that's sort of like our mole to mole relationship. So we'll take our 0.0253 moles of electrons, use our half reaction here. 2 moles of electrons gives us 1 mole of calcium. So we'll take that and divide it by 2. Going to give us 0.0126 moles of calcium. And in this case, we're interested in how many grams. So we could use our molar mass from the periodic table, which is 4008 grams per mole of calcium. Moles are going to cancel. And we'll call it 0.507. 0.507 grams of calcium. So if we ran this guy for 1.5 hours, we should get about a half a gram there of calcium basically coming off. Any questions on that there? Now, if we were interested in chlorine, we could do pretty much the same deal. We could pick it up with our moles of electron. We could go to chlorine's half reaction, and we see it's actually a similar type of setup there. We got 2 moles of electrons gives us 1 mole of Cl2. That's going to give us 0.0126 moles of Cl2. Since chlorine is a gas, you might have had some temperature and pressure information, which could let you go into the ideal gas law. Or if you're interested in grams as well, you could just use the molar mass of Cl2, which in this case would be about 7090. And if we collected our chlorine gas in grams, we should come out with like 0.89 grams or something like that. Any questions on any of those steps there? All right. So the goal here is to kind of get yourself to moles of electrons, use the half reactions again to figure out kind of moles of electrons to moles of whatever you're looking for. And then obviously you could solve for it. Any questions? Oops, on that one? All right, so why don't you try one here? Let's do our water example here. So we will have a current of 1.26 amperage pass through an electrolysis cell containing sulfuric acid for 7.44 hours. We are looking for the volume of gases generated here at STP. So this is the electrolysis of water, and clearly it says nothing about water in this case, right? Which is again very common. And again, the key word here is sort of containing sulfuric acid is kind of the key word that you're kind of going to be doing the electrolysis of water. So why don't you give it a go? I will give you the half reactions that we saw previously there. And in this case, we are running the cell for 1.26 amperage. I think it was 7.44 hours. And we're at STP. We're looking for the volume of hydrogen and oxygen gas. By the way, STP stands for standard temperature and pressure, right? And those are actual values, right? So temperature is 273 Kelvin. Pressure is 1 atmosphere, by the way. All right, so take a few moments here, calculate the volume of both of those gases that should be generated in this particular case. All Okay, so let's take a look since we're getting towards the end here. So the beginning of this is going to be pretty similar to the last one. We have really our amperage, how long we're running the cell for. So from that, we could get our Coulomb charge, and then we could use Faraday's constant to get our moles of electrons. So doing that, we're again going to convert our hours into seconds. So we're in the correct units. And again, an hour is 3,600 seconds. And we'll take 7.44 times 3,600, 26,784 seconds. Remember, this is the same as 1.26 coulombs per second. So we're going to use that to get to our charge. Those guys are going to cancel, and that will get us about 3,374.7.8 coulombs of charge. We will then divide by Faraday's constant here to get to our moles of electrons. So 3,374.7.8 coulombs. Dividing by our Faraday's constant, 96,500 coulombs per mole of electrons. Coulombs will cancel. A little division here. Gonna give us here 0.3497 moles of electrons. Any questions up to that point? At that point, we can now kind of go into our half reactions and get our moles of both the hydrogen and oxygen in this case. So the moles of hydrogen using the first half reaction or the second half reaction there. We see that if we multiply the 4 in, we will have 4 moles of electrons, give us 2 moles of hydrogen, or that's also a 1-to-2 relationship if you want to use it like that. So we'll do 0.3497 moles of electrons. And again, it doesn't really matter if you reduce it down or not. It will come out to the same number, obviously, moles of hydrogen. And that's going to get us there 0.175 moles of hydrogen. We'll do the same thing for our oxygen. Going to here, it is a 4-to-1 relationship there. So 4 moles of electrons give us 1 mole of O2. So we'll use our moles of electron. We'll use our relationship there. 4 moles of electrons, 1 mole of O2. Gonna get us there 0.350, I'll call it, moles of oxygen. Any questions up to there? Now that we have the moles, we also have the pressure, the temperature. So we really always have R as well, which is a constant. Here we would use our ideal gas law if you like. So using our ideal gas law for our hydrogen, for example, would be P equals nRT, which means V is nRT divided by P. So our moles of hydrogen is 0.175. Our R is 0.08206. Our T here is 273. And RP is 1 atmosphere. Everybody should cancel here except for liters, which is good. And that's going to get us there 0.175 times 0.08206 times the 273, 3.92 liters of hydrogen gas would be produced. We can also go into the same equation here for oxygen. So the volume of oxygen would be the moles of oxygen, 0.35. Our R is still the same. Our 273, and once again, our 1 atmosphere. And in this case here, will get us here 7.84 liters of oxygen in this case, right? Now, any questions on that there? I feel like I switched them around somewhere. There we go. Yeah. What's that? I should have. I feel like I didn't do that. Is that what I'm missing? I feel like I'm missing something here. It didn't feel right because we should have twice as much hydrogen than oxygen in this case. Thank you. I think I just rounded that number. I said it. I don't think I wrote it right. Thank you. I felt it was wrong there for a sec. All right. So sorry about that. I wrote it. I don't think I actually did. I guess that's good they invent erasers even for these things. Let's try this again. All right. Now you probably actually want to divide it, I suppose would be good. There you go. I feel like I did. I just didn't write it. All right. So we'll go with the corrected. We'll just cut that out of the video later. 874 moles of oxygen there. We'll pop this in here correctly. There we go. I did go opposite pretty good, though. It's got twice as much oxygen as hydrogen. I think I did something not so right there. All right, 0.08206 and 273. That looks maybe a little better. There we go. 1.96 looks a lot better. Like I had a course the first time. If you closed your eyes. Yes. Here we do see the correct relationship there. We have twice as much, right, hydrogen as we do oxygen there. Thank you, Justin. Yeah, I wrote it. Forgot to actually do it. Also, by the way, this was STP, right? Which means if you did not want to use the ideal gas law, this is a situation, provided you take the right moles, right? Moles of oxygen that you could use 1 mole of any gas at STP is 22.414 liters. Should get you there as well. So that's where you could use that conversion without having to use ideal gas law. A reminder that it does have to be at STP conditions for you to use that conversion there. That looks much better, I think. Thank you. Other questions on that there? Well, clearly we should lay it up there, I think, for today.